Let me begin with a word of prayer. Oh, is the audio bouncing? Can you see the bar going la 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 la? Yep. Okay, excellent. Heavenly Father, we thank you for this day again, Lord. I thank you for these students and just ask you to bless this time we have together, Lord. In your name I pray. Amen. Okay, so let me just try to go kind of quick through these. So problem 1 was we had x squared plus 4x plus y squared minus 12y. So group 1 completed the square, very good, and realized it's a circle with radius the square root of 40. Problem asked for counterclockwise, so they wrote down, x plus 2 is root 40 cosine t, y minus 6 is root 40 sine t, right? Just like an example we did in the previous day. And there you go. This is the answer to part A. These are the scalar parametric equations, although I really should also say 0 less than or equal to t less than or equal to 2 pi, right? At least if I want to cover the circle once. I mean, in principle, you might want a path which covers the circle 20 times. Then what would you do? Counterclockwise. What would you do? To go 20 times around, what would you choose? Like 0 to what? 0 to 80 pi, right? 2 times, 40 times. Wait, did I say 40 or 20? You guys are right. You said 40, right? My bad. Okay, sorry. So you could, of course, you could increase the domain of the parameters if you wanted to cover the circle more times, but if we just want to cover it once, 0 to 2 pi will do just nicely. And then the vector parameterization, we just put these in a pair. It's minus 2 plus root 40 cosine t, and 6 plus the square root of 40 sine t. There's the, again, for 0 less than t less than 2, that's the vector parameterization for the curve, right? And then we also needed a sketch. So the sketch of this curve, it's centered at minus 2 and 6, which they have. There's the center of the circle. That's not actually a point on the circle. Square root of 40 is somewhere between the square root of 6, the square root of 36 and square root of 49, like 6.5-ish. So it's a little bit below, something like this, roughly speaking. So that's problem 1. Okay. Any questions about this? All right. Problem 2 was an ellipse. We had x squared plus 8y squared equals to 1. So this is just a reminder. I wrote this up here. So if we're confronted with an equation of the form x squared over a squared plus y squared over b squared equal to 1, this is the standard equation for an ellipse, right? Which goes through plus or minus a on x and plus or minus y on b, plus or minus b on y, rather. So this one here, right, like they said, it's just this part. And what I said it was left moving, or I said it was clockwise. So they've got it going this direction. Very good. And so they've got x equals to sine theta, y equals to 1/8 cosine theta. So they're using theta as the parameter, right? So theta is playing the role t did in the previous problem. You could make the parameter any letter you like, right? T is not, like, it doesn't have to be t. You could use lambda or theta. Theta is nice because it has with it the idea of the standard angle, right? If we're thinking about theta being the standard angle. Oh, I shouldn't do that, though, because, well, theta is not the standard angle here, right? Because it's running clockwise. Anyway, let's see here. If you're going to use sine theta and cosine theta, if that's your choice, then what do I need to do to get from here to here, like that? So at the initial point, I need sine theta equal to what is this point? 1, right? And I need, so sine theta not equal to 1, I need that 1 over 8, 1 over square root of 8. Cosine theta not equals to 0 to get this point. This point is 1, 0, right? And on the other hand, I need sine of theta 1 equal to minus 1. I need 1 over the square root of 8 cosine theta 1 to be equal to 0. If I'm going to use the parameter domain theta 0 less than or equal to theta less than or equal to theta 1, what I'm posing the question is, how do you figure out the starting and ending angles for problem 2? You see what we have to do? We have to figure out a theta 0 and a theta 1, which solves those equations I just wrote in black. Can you tell me what theta 0 should be? Yeah.
Would it be negative pi?
Theta 1 would be negative. Which one would be theta? Theta 0 equals to what? Theta 1 equals to what? So you said theta, I think, how about theta 1 is maybe minus pi over 2 would be good, yeah? I think minus pi over 2 would work. If we take the sine of minus pi over 2, we get that. I mean, that solves those equations, right? And how about theta 0? Are there other solutions to theta 1 besides that? What else could you use? How about 3 pi over 2? We could also, that's another possible solution, right? There's, in fact, infinitely many solutions to this, right? If you take a solution and you add 2 pi, it's still going to be a solution because sine and cosine are 2 pi periodic, right? How about the other one, the theta 0? I think we could do pi over 2, right? Pi over 2 would work. Cosine of pi over 2 is 0. Yeah? Or like, you know. So I think what I would do if I was doing this problem is I would say pi over 2 less than or equal to theta less than or equal to 3 pi over 2. That would be the domain I would give for the parameter there, personally. You could just as well go minus 3 pi over 2 to minus pi over 2 if you liked. But I think that's a good choice. Now, what's the vector parameterization here? R of theta is sine theta, comma, 1 over root 8 cosine theta. Again, with the same parameter domain. Any questions? So why did you guys put sine on the x and cosine on the y? Would the reason possibly be because that's what I did to get a clockwise orientation the other day? I mean, that's a respectable reason. That would be the reason I would guess, right? I mean, we've seen that gives a clockwise orientation if we put the sine on the x and the cosine on the y, right? Yeah.
Wouldn't the theta 0 less than equal to theta, why do you need to...
To specify a parametrization, we have to give formulas which solve the equation, right? But we also have to specify the values that the parameter can range over in order to hit the curve in question. So my point was my initial point is 1, 0. My final point is minus 1, 0. So I need to pick values of theta, which I've called theta 0 and theta 1, which solve this and that, respectively. We don't even think about it for many problems, right? Like this one, we just said, oh, 0 less than t less than 2 pi, because this is like, we know what's going on here. We've seen this before. It's going to work. Your problem 2 actually required some thinking on the question of what to pick for the domain of the parameters. Problem 3, here you were asked to parametrize the part of y equals x, which is bounded by the unit circle, which is just a really weird way of saying parametrize this line segment, right? So what they did was they figured out that the line segment goes between what was it? Well, not unit circle, it's the radius 2 circle, isn't it? Okay, so let me just redraw the picture again. So what's going on here is this has radius 2, right? Which means that we're looking at root 2 and root 2 like that. Is that right? Okay, yeah. Sorry, I'm having Pythagorean doubts for a second there, but very good. And so you're trying to parameterize this as you guys have drawn this line segment here, which you've made it blue. Very nice. And so your scalar parametric equations were minus 2 root 2 plus 2 root 2t for 0 less than t less than 1. And you guys used the, you did the vector one first. Very nice. I like that. So these points are what? Negative root 2? Negative root 2? And so that's the initial point. And the terminal point up here is square root of 2, square root of 2. So they use the thing I introduced, what was it, I forget when it was, Friday. So the point plus t times the final point minus the initial point, this parametrizes a line segment, right? If we let t range from 0 to 1, this is the standard trick. They just identified the points that they're going to do q and p and put it in. Does that make sense? Yeah. All right. This one here, problem 4, again, complete the square. Once you complete the square, what we're looking at is the difference of squares, right? This is a hyperbola, and it has center for 0, right, as they've drawn. And so you've got these asymptotes off that the hyperbola is going to go between. And I said x greater than 0. Oh, well, that's not really. Are you guys? Is my problem nuts? Let me think about this for a second. If we put x equals to, oh yeah, you guys are right. That's what it looks like. So, yeah, sorry, my instructions are not awesome here. I wish I'd gotten around to you guys. I couldn't get you in the corner. Like, this problem is not well posed. What I should have said is, like x greater than 4, you know, and upward. So this is what I meant. This is, you can cross that out, guys. That's unfriendly. To put x greater than 0, that's not friendly. That would require 2 different cases. And the question would be viewed as ambiguous by some students, and they'd be right. You were confused? That's good. You should be confused.
So were you asking for just the top part of that?
I wanted just x greater than 4. I wanted what you guys did, actually. So you guys somehow saw the right question despite it not being asked. Very good. So I think your answer is right. So you got x equals to 4 plus cosh, and y is equal to, oh, okay. Now, can we check if they're right? Let me write it down, guys. They said x is equal to 4 plus 4 cosh t, and y is equal to 4 sinh t, right? Let's check if these scalar parametric equations are right. We need to check, is x minus 4 squared minus y squared, what's that equal to? Well, this would be 4 cosh t squared, right, minus 4 sinh t squared, because the 4's cancel, right? The plus 4 and the minus 4 cancel in their parametrization. And then what? Then we can factor out a 16.
I'm sorry.
Uh-oh.
Plus 4 is only plus 4 on the x.
Oh, yeah, but I'm trying to say the 4 cancels on the x, but that's all I meant to say. I'm plugging in your formula here and here into the given equation. After, well, not the given equation, but your reformulation of the equation, which is better to check. Yeah. So I'm saying if I plug these into there, it should work. If you guys are right, and I think you guys are right. So the 4, this plus 4 cancels with that minus 4. Give me, it's fine. Give me 4 cosh and 4 sinh. But then we square them. We get 16 times cosh squared minus sinh squared. But what is cosh squared minus sinh squared? That's 1. So we get 16, which is, in fact, so there you go. This actually does parameterize that curve. Is it upward moving, as I asked for? Well, how would we check that? What would it mean to be upward moving? It would mean that dy dt is positive. Is dy dt positive for this parameterization? What's the derivative of y? Well, it's 4 cosh t, which is, yeah, that's always positive, right? In fact, the y velocity is always at least 4 in this curve. So very good. Problem 5 was what? Well, you guys have the sheet, right? So it's the line segment from 3, 4 to 6 minus 10. Thanks. And here's a picture. What is this? What's this thing here? Why is there an 18 there? I'm confused. So the picture I was hoping for was like this. Something like that. Here's the line segment, right? It goes from 3, 4 to 6 minus 10. And right, again, you found it convenient to do what? Do the vector to answer part B first, right? Because the vector viewpoint is the easy way to find parametrization of a line, right? We use this standard trick. So P is 3, 4, Q is 6 minus 10, minus P is Q minus P is 3 minus 14. Very good. So R of T is 3, 4 plus T times 3 minus 14, right? This P minus Q, by the way, in terms of, if you had high school geometry, maybe you use this for it, right? It's the direction vector from P to Q. It's the displacement vector from point P to point Q, if you like. Yeah. And yeah, this, and then, okay, but 0 less than or equal to T less than or equal to 1. And there we have it. This is the vector parameterization. Okay, so you got 3 plus 3t for x, y is equal to 4 minus 14t. Very good. This is a good answer for part A. All right. So in the world of all possible questions for test 1, if I ask you to parametrize a line segment, should anyone miss this problem? Heavens, I hope not, right? Like this is, you should be like, please sir, may I have another? Let every problem on test 1 be this, right? I mean, this is a very, pretty cut and dried thing. Yep. What is the what? For part. So this is A right here. These are the scalar parametric equations. Oh, you can't read it. I gotcha. Minus 14t. So what all they're doing, I mean, all I would do is just expand this out, expand the vector answer out, and just pick off the x component and pick off the y component separately. That's how I'd get them anyway. Problem 6 was, and I haven't stated these quite right? I really should have said y equals cosh x for 0 less than or equal to x less than or equal to the natural log of 3. To emphasize, I'm thinking about the graph. It's the graph of the function f of x equals cosh x, all right? And so you guys told me x equals t, y equals cosh t, 0 less than t less than log 3. Perfect, great, scalar equations, scalar parameterization of the graph. And then for the vector, you've got t cosh t, 0 less than t less than log 3. Very good. And I'll zoom in on your answer here. So you said we start at 0, 1. And then it's parameterized this way, because it's right moving, right? If we put x equals to t, that makes it right moving. All right? And then we get over to here. This point is natural log of 3, cosh of the natural log of 3. And they've got 5/3. Do you guys know why that is? Why is cosh of the natural log of 3? What is that? That's 1/2 e to the log 3 plus e to the minus log 3. So what's e to the log 3? 3. And this minus, what happens to it when we bring it inside the logarithm? I can erase this, right? And trade it for that, right? That's properties of logarithms. P log a is log of a to the p, right? So e to the log of 3 to the minus 1 is, so we just get a 3, otherwise known as a third. What's 3 plus a third? Ten-thirds, right? So we get 1/2 of 10/3, which is otherwise known as 5/3. We have a winner. Very good, 5/3. So, A little bit of hyperbolic background there for you, but very good, guys. Any questions about this one? Problem 7, I didn't state a domain for problem 7. So, by default, when we're talking about a graph, if the formula makes sense for all reals, it's customary to take the domain to be the whole reals, right? So here we had, okay, so we had y equals to x cubed. I was having trouble finding the original problem. I know I just wrote it, but I forget. So that's actually the graph which I intend to give there. And so x equals t, y equals, that's an f of t. But, for this problem, I'd really like to see you write t cubed minus 5t squared plus 6t, okay? Yeah? So there's the scalar parametric equations for t in the reals. And, this one's good. I know this is just sort of your template, right? This is just the sort of the template for how you set up the solution, right? And so we got t cubed minus 5t squared plus 6t. Very good. Oh, this, no. That was not given in the problem. If that was given in the problem, that'd be a different curve. That would just be part of this cubic, right? This is, of course, a cubic. If we look at x cubed minus 5x squared plus 6x, you guys remember this is x times x squared minus 5x plus 6, right? Which is x times x minus 2 times x minus 3, which means what we're looking at is x-intercepts of 0, 2, and 3, and it looks something like this. So this is a picture of what you're doing. Sometimes it's increasing, sometimes it's decreasing. It's got a point of inflection. It's concave up some places, concave down in other places. This is a very interesting curve. But there's a picture. Yeah. All right. Well, I hope this exercise was helpful. I think it would be productive for us to look at my notes for a bit here. Oops. Come on. Eventually it'll wake up. Let's see here. Go to sleep. I wonder if I have my laser. So I have posted these notes in course content, right? So I've encouraged you a couple things in this class. The one is to have I have to change to, I'm in the wrong HT. Come on, there we go. To have, it's healthy for you to have a calculus book of your own, perhaps Stuart, but I do follow the notes in some sense, right? So it's also helpful to look at these. Remember the course planner? In the course planner, I show you, oh, that's the wrong course planner. Maybe this one? Ah, there you go, you guys. So, of course we lost day 1 to snow, which is, we're still feeling the effects of that actually. Where we are at the moment, of course, is here, right? I actually talked about physics of motion in 2 dimensions previously, right? So we're a little bit off my plan, but I decided, because I wanted to spend more time on just examples for parametric curves since you guys asked. But I will soon, probably tomorrow, I'm actually going to start on integration by parts, all right? So I'd like to show you some examples of arc length and try to answer the questions that I've posed on the worksheet in the time that remains today, all right? Every one of those is a pretty easy question. You just have to understand how to kind of attack it. And so one of the things I wanted to show you is just that. If I could get back to my note. Oh, there it is. So first of all, chapter 12, and again, this is posted in course content if you hadn't noticed already. I have, a bunch of examples. I have actually defined, I've written this on the board already, right? But like, this is what a graph is. Here's some examples of graphs. Some things are graphs, some things are not. Like a circle is not a graph, right? Because, why? It fails the vertical line test, right? You actually need a pair of graphs to graph a circle. This, if you run sine vertically, it's not a graph, right? But actually, the green piece is the graph of the green piece. The green piece is the graph of inverse sine as it happens. Anyway, I'm not trying to. I just wanted to point your attention to these notes. These are there for you to kind of scan through. If you need more background about it, what graphs are and what different equations look like, then here's some things for you to read, okay? Because some of you have expressed indecision about knowing, like, what's a circle and hyperbola and how those equations are viewed. I've got lots of examples in this chapter, and I've got some weirder things, right? Like here, this equation, if we look at that equal to 0, this is the solution set of this monstrosity, right? It's not hard to write down equations which have really, really weird-looking solution sets. This would be an example of something that I wouldn't put on your test, right? But I want you to realize there's tremendous freedom both in the parametric and the equation viewpoint in what you can write down for curves. There are curves that you haven't even imagined yet, which mathematics allows for. All right, anyway, moving on. Sorry, let me scale back here a bit. In section 12.3, I have a clumsy definition of what a parametrized curve is to start with, and then I have a bunch of examples, like here's a circle. Every time I think about a parametrization, I think actually about a map from the real line to the plane, and I'm taking this line, in some sense, stretching it over the circle. That's what the parametrization is. It's like laying down the line over the circle. And I'm tracking these points. These colored dots are mapping to the dots in the order that they're represented. Another example, this one, same circle, but really different parametrization. Here I have e to the t and as the input for sine and cosine, right? Anyway, I don't want to go through all these. Just the point is, you should glance through them. If you're still feeling uncomfortable with what a parametrization is, perhaps reading these would be helpful to you. Yeah. So I have many examples of circles, line segments. Here's a box discussing the woe of what a parametric viewpoint is. Here's a bunch of examples on how to find the Cartesian form from the parametric form. Here I have a bunch of examples where I actually eliminate t from a given x and y equation, right? It's like start with, I think example 12.4.1 I already did in here. It was my first example. So anyway, if you're thirsting for more examples of, here, this one, I have x equals cosh, y equals 2 sinh plus 3. I'm like, find the Cartesian equation. So what do? I solve for cosh, I solve for sinh, I look at cosh squared minus sinh squared is 1, and there you go. That's the corresponding Cartesian equation, right? And my point is, you should read these, yeah? Anyway, so perhaps if you're missing out on something, that chapter 12 will be helpful to you. Chapter 13, I start with vectors, all right? We've done that. So the difference, of course, between a, it's kind of small, yeah? Let me get rid of this nonsense over here. So, of course, a point we think about as a point, but a vector is a directed line segment, right? So where you attach the directed line segment is kind of up for grabs. In physics, we talk about this a lot, right? You can move the vector around, right? We allow ourselves to move the vector. That's called parallel transport. But by default, I think about vectors being attached at the origin, right? But here's some pictures of the vectors and the components. All right. These things we've gone over. Here is the boring definition I mentioned. This is how we differentiate a vector. This is how we integrate a vector over time, right? So nothing too surprising there. We actually did an example of that last class, right? Some theorems. If we differentiate a vector-valued function, a little bit much. If we differentiate this with respect to time, we get that. So like there's an FTC1, here's FTC2. Like if we integrate the derivative of a path, it's the difference of the path at the endpoints. Here the output's a vector, all right? There are also rules for differentiating paths. Here's like the derivative of a sum is the sum of the derivatives. If you had a function times a vector, you get this product rule. We can pull a constant out like that. The integral of a sum is the sum of the integrals, and we can also pull a constant out of the integral. Nothing terribly surprising here. So I have talked about these notes, but I don't think I have emphasized enough to you guys that I would like for you to be looking at these, right? Because some of you are asking me questions, which indicates to me that you're not aware these exist, right? So please look at these if you haven't been already. For those of you who have been looking, my apologies if I'm wasting your time at the moment. Now, so this is a very interesting example. Here we have a position which is r cosine omega t, r sine omega t, all right? So what's the significance of this omega? In physics, we call that the angular velocity, right? It's like how many radians per second. And so when you differentiate that, we end up with an r omega times that. What can you tell me about the thing sorry, there's no laser in my finger. This vector here, bad choice. How long is this vector? What's its length? Sine and cosine? Square root of sine squared plus cosine squared, right? Otherwise, square root of 1. This is a unit vector. So the magnitude of the velocity is straight up r omega, right? So the speed of this curve is the radius times the angular velocity. This is a particle going in constant speed circular motion, right? And that's why the tangential velocity is r times the angular velocity, and the acceleration is also just r omega squared. This might be familiar to you from physics. It may not. I don't know. I have some pictures. There's a picture of the one I was just looking at. So constant speed, circular motion. We could actually picture the velocity and the acceleration. Like, no, I'm going to stop using this. That's going to be burned into my retina. So, center-seeking acceleration. So this is constant speed. So the acceleration is always just pointing to the center. Velocity is tangent, goes around, right? What happens when you have non-constant speed circular motion? I have a picture about that a little bit later in the notes. The next thing up, though, I did this rather famous case, which is just, this one, right? Oh, no, wait a minute. Projectile motion, right? So the motion is just governed by the constant acceleration of gravity. And in that case, we can start with the acceleration up here, right? And then we can integrate. We integrate once, we get the velocity. We integrate again, we get the position. And so these are the famous kinematic formulas written in vector form. The initial velocity plus 0 minus gt. I integrate again from 0 to t. I get the initial position plus t times the initial velocity plus this acceleration term minus 0 minus 1 half gt squared. So that constant velocity in the x direction and the y velocity, it goes up and it comes back down. Here's a picture. So the red dotted path here is the actual trajectory of a particle like the marker I just did. And at every point, the acceleration is in blue. It's just 0 minus g, right? Very boring. Always just negative downward acceleration. And the velocity is kind of interesting, right? It's changing. But if you looked at all these green vectors, if I did it right, they should all have the same horizontal component, right? Assuming no friction, the horizontal velocity just stays constant as the gravitational acceleration just acts on the y component to the velocity. Also, the length of this vector should be the length of that vector, right? If we're assuming no friction because energy is conserved. So like if the potential energy is the same, then the kinetic energy should be matching if energy is conserved. And kinetic energy matching means that the speed at the start and the end should be equal. You're not supposed to know that right now in Physics 231. I may have just spoiled the course for you. I'm sorry. There's this thing called energy you'll learn in a couple weeks, and it makes all the problems you're doing right now way easier to solve. If you want to cheat on test 1, go ahead, study energy. Use it now. It makes it much easier. What's that? Oh, okay. All right. Now, furthermore, the arc, if we calculated the arc length of a physical path, that would be the, I think I call that distance traveled. All right. So like, what I'm saying is, if you go in a circle, right, all the way around, the displacement is 0, right? Because the initial and the ending point are the same point, but the distance traveled is what? It's all the way around. So that would be like 2 pi r for a circle, right? So distance traveled is really just arc length, like this. We calculate that. Now, I will warn you, that, sorry, so this was the, the other example I was mentioning with non-constant speed motion. Here I allow theta. So here I've got r cosine theta, r sine theta. This parameterizes a circle, but I'm allowing theta to be a function of time. In particular, theta is quadratic in time, right? So this would not be constant speed circular motion. It's like variable. It's actually accelerating. It's like you're going around a circle, and you move faster and faster and faster and faster and faster and faster, supposing that this alpha is positive, right? So this would be actually, and I'm assuming alpha is a constant, so this would be constant angular acceleration circular motion is what this problem is studying. So I calculate the velocity, I calculate the speed. The speed is still actually pretty simple. It ends up being r times the absolute value of omega plus alpha t. And then I integrate the speed to get the arc length, like that. Here's a formula for the arc length. It's just r times the initial angular velocity times time plus 1/2 r alpha t squared. This is something you'll learn in Physics 231 towards the end when you study circular motion. And then the acceleration has 2 pieces in this problem. It's got the center seeking part. Yes?
Is capital R the radius of the circle?
Yeah, capital R. What else are you thinking it might be?
I have no idea.
Oh, okay. You thought it was what? Oh, well, yes. We use lowercase r for the polar radius. But sometimes I'll use a capital R just for like I'm thinking of a particular circle and the radius of it being r. So I usually, when I'm thinking about capital R, I usually I want it to be a constant. But, it's not written in stone. But yeah, we use lowercase r for the polar radius. So this problem, there's 2 pieces to the acceleration. There's the piece which is like cosine sine. So that's center seeking. That's the centripetal part of the acceleration. And now, since I've let theta actually be accelerating, there's also another piece. There's a tangential piece, this minus sine cosine, right? So you could draw a picture of it. The tangential piece lines up with the velocity to the curve. The centripetal piece is center seeking. We've got both of them in this problem because this wasn't a constant speed circular motion. There's both pieces. And these things, of course, we can carefully study with calculus, right? Sorry, I want to finish this show and tell as fast as I can because I want to get back to writing on the board. But I just have a few things to mention here. This you should not understand right now. Example 13.3.8 should be complete mysterious. It's pure dark magic at the moment because I'm doing this. I'm solving the integral. This integral that I'm doing here, it is just not something you know how to do at the moment, all right? So we learn how to do that kind of integral next week, actually. But this integral is actually a little bit much even then. When I started this integral, I didn't think I was going to find a formula, but this, for what it's worth, is the formula for the arc length if I took this marker and I threw it with initial x velocity of v0x and initial y velocity of v0y. If I did that, ignoring the spinning of the marker and such, just tracking the center of mass of the marker, that would be the length of the parabola that it just traced out would be given by this formula. It's kind of horrible. This formula you will never see in Physics 231. It's not something we would ever. Actually, I should try to get Dr. Scambortis to put it on his final or something. I don't know. I'm just kidding. He doesn't listen to me. Well, he might. I don't know. All right. Finally, after I'm done with the physics, at the end of this chapter 13 in my notes, I talk about geometric analysis in the parametric setting. Many of the questions I pose on your worksheet are answered in section 3.4. All right? But what I want to do is I'm also going to say at the end of this chapter, I have multiple examples of arc length integration. So the arc length integral, I've already written on the board. It was the integral of the square root of dx dt squared plus dy dt squared. That kind of integration, many of the actual ones that you'll confront at the moment, you don't have enough understanding of integration to do them. So there's going to be a payoff after we learn some more integration. You're going to be able to do more arc length problems explicitly, but that hasn't happened yet. So I'm just trying to warn you, if you actually just go to try to calculate the arc length right now, it may be too much. It may be beyond your integration skill. Those problems are at the end of this chapter here. Well, example 1 you could do, but anyway, I'm going to put this away. So what I'm covering right now is if I haven't remembered wrong, it's either section 13.3 or 13.4 of my notes. And roughly speaking, that is geometry and parametric curves. So what were the questions I posed on the worksheet? First of all, I asked, what is dy dx as a function of the parameter? So we're going to consider x equals to, let's say, f1 of t, and y equals to f2 of t, just for the sake of discussion, okay? So first of all, what would dy dx be? So it turns out, if you analyze this, that it turns out that dy dx can simply be calculated by dy dt divided by dx dt. All right? Or to be more specific, what I mean by that, of course, is df1, or excuse me, df2 dt divided by df1 dt. This is actually how we can calculate the slope to a parametrized curve at a given point. Let me explain to you why that is. I can explain. If we have our vector parameterization, R of t, is, f1 of t, f2 of t, right? And we calculate dr dt, what does that give us? It gives us this, right? If we were to picture this, what does it look like? Take a point, right? On that point to the curve, the velocity vector, what's it look like? It points along the tangent line, right? So if I was to picture that, this is the r prime of, let's say, t naught, to give a, let's suppose that this point here is at r of t naught. So what's the slope of that line? It should be the ratio of the y component and the x component of that vector, the velocity vector, right? So if you look at it, this is r prime of t naught, right? But what is this? Well, this is df1 dt at t naught, and this vector, this length of this over here would be df2 of t naught, right? So the slope would be y over, right, rise over run, which is exactly df2 dt divided by df1 dt at t naught. It is kind of amusing to think about this as just being because the dt's cancel, right? But that's not a derivation. That's just a fortunate quirk of the notation, yeah? So for example, specific example, if we had x equals to t squared and y equals to, say, t e to the t, all right? And then let's, what is dy dx at t? It's d dt of t e to the t divided by d dt of t squared, which would be what? It's t, I think it would be t plus 1 times e to the t divided by 2t. So what would the slope to this parametrized curve be at time 1? What do I got? I got 2e divided by 2, right? So the slope would just be e. What's the equation to the tangent line when time equals to 1? How about y? So first of all, this marker is garbage. What point are we at when time equals 1 for this curve? So we're at where? 1, 1e, right? So this is the point 1. 1 squared is 1, yeah. 1 times e is e. So this is 1e on the curve. So the tangent line at 1e to this curve would be y equals e plus e times x minus 1. This would be the equation to the tangent line. What if I wanted a parametrization for the tangent line? Well, the tangent line at t naught, we could parameterize by this. L of t equals to r of t naught plus t times r prime of t naught. So this is like a general template for writing down the parametrization of a tangent line to a given path at the point, at t naught, r of t naught is on the curve, right? So for this one, what's r of, for the example I'm looking at the moment, what's r prime of 1 equal to? It was 2e actually, yeah? So for what it's worth, here's the parametrization of the tangent line. It would be r of t is, what was my point, 1e plus t times 2e. There you go, that's a parametrization for the tangent line at the point. Towards the end of your list of, on the worksheet sheet, I ask what's the parameterization of the colliding tangent line, right? I should talk more about that some other day. There's not enough time to do that justice, but we'll come back to that. I mean, all that essentially means is you replace t with like t minus 1. But anyway. The other thing I'd like to answer in the time that remains here is, how do we calculate d squared y dx squared, right? So, by the way, once you calculate dy dx, I mean, so this is clear as everybody. I mean, if you give a path, you can calculate dy dx. It's not a big deal, right? dy dt divided by dx dt, right? So this is a little bit surprising. This one is, it's not, I mean, wouldn't it be great if it was just take y prime prime over x prime prime, but that's not what it is. It's not what it is. This is actually d dt of dy dx of t. Well, excuse me, that's not right either. Good grief. This is d dx of dy dx, right? So we have to look at that as d dt of dy dx of t divided by dx dt. For our specific problem, did it actually go in? I'm shooting blind. It's just an accident. Yeah. So d squared y dx squared at time t would be d dt. So what was dy dx? We figured it out over there. It was what? Oh, why? Why did I sign up for this? So t plus 1, oh goodness gracious, what's wrong with me? Divided by 2t, that times e to the t, right? And then you got to divide by d dt of x, which was t squared, yeah? I'm not going to do it, but that would be d squared y dx squared as a function of time. Now, why would you want to know any of these things? Obviously, we're interested in the slope of the curve at a point, right? Fine, easy enough. How about the second derivative? What does this tell us? This tells us if it's positive, it's concave up. If it's negative, it's concave down, right? Other things you might ask about a path, like does it have horizontal tangent? Does it have vertical tangents? How would you answer those questions? You look for where dx dt were 0 or dy dt was 0, right? If dy dt was 0, you'd have a no change in y, horizontal tangent, right? If dx dt was 0, you would have a vertical tangent, right? Assuming the other one was non-zero. Anyway, I'll shut up, and hopefully tomorrow, I think I'm going to just go ahead to integration at this point. I'm sure there are still questions about parametrizations, but we should go on. So, the real issue is have I answered these questions. I think I still have to talk about the colliding. Okay.
You said T naught a lot.
Oh, did you stop the recording?